I'm going to share my screen. Can you folks let me know if you can see my screen? Okay, how about now, Rahul? Okay, awesome. Cool. Just 1 second. All right. So today what I'm going to be talking about is understanding benchmarks. And I was kind of going back and forth on thematically, should I just kind of talk about what what does it mean to actually benchmark a system? And like, do we talk about this specifically in the context of like, the class for IoT related specific systems? But I thought I'd just kind of take this opportunity to help you folks understand kind of like how we think about benchmarking machine learning systems. And I'll explain what I mean by benchmarking and all that good stuff. So I'm going to intentionally paint like a rather broad picture of what it means to kind of, build benchmarks and all that stuff, because I think it's very relevant. It's in the sense of like it spans the entire spectrum from large scale data centers down to TinyML systems. Whatever you talk about, the fundamentals end up being the same. And I think that personally, if I was teaching my class, that's kind of what I would want to pick. And so that's what I'm going to talk about today. So let's see. So when do benchmarks become important, right? Benchmarks are basically this idea that you want to be able to compare different systems. As simple as that. It's much more sophisticated in reality, but we'll take that very simple definition that benchmarks means I want to be able to compare systems. Now, why do you want to compare systems? Well, it's like if you kind of look at the machine learning ecosystem right now, it's really booming, right? Way back from like when AlexNet came in 2012 to kind of where we are right now. There's a lot of customized hardware that we're seeing all around the front, right? So you have, obviously GPUs. Every generation of a GPU is much more capable. People are starting to build custom hardware. Google has been building TPUs practically since the 2012 days, in fact. And there's lots of other hardware that people are specializing. Like, in fact, there's a company that I advise that specializes in only building the chip just for the transformer architecture, right? So people are getting extremely specialized. And one of the reasons for actually doing all this hard work is really because, it's starting to actually become quite critical to deliver high performance. So if you look at the traditional Moore's law, which is the doubling of transistors every 2 years, roughly speaking, that's been our bedrock sort of foundation in terms of what gets us better performance from year to year. But if you kind of look at the, machine learning application ecosystem, right? If you're looking at computer vision or NLP or speech, speech recognition and so forth, the computational demands for these applications have actually been, much larger than what traditional computing would actually give us, right? So, CVNLP and so forth has been demanding about 15x improvements every 2 years. And if you look at when transformers kind of came into the play, things have just exploded, right? Every 2 years, there has to be almost a 750x increase in computational capability with respect to like, the chat GPTs and all these things that we take for granted. Now, when you're talking about scale of systems at that level, every decision that you make as to, hey, do I pick system X or system Y, because it's extremely critical. This is where people have a real sort of thirst to want to understand. How do I compare any two systems? Now, this could be big data center style GPUs, or it could be like, the really small TinyML kind of systems that we're talking about. There's an incredible amount of specialization that's happening. Now, why is it that it's so hard to actually compare two systems, system X versus system Y? It seems like it's pretty simple. You look at some sort of specifications, and you might say, okay, well, this thing has a little bit of a throughput, that thing has another level of throughput, and you can just measure performance in terms of time. That's kind of naively how we would think of benchmarking if we kind of talked about benchmarking historically, the way we built CPUs and all those kinds of systems. But as I'll kind of go through today, there's a lot of embedded complexity with these kinds of machine learning models, right? There's an incredible level of coupling between what's actually happening at the task level down to how we actually do innovation at the lowest levels of the system stack, right? So you have to understand what's the task, what model are you running, what's a data set, batch size, quantization, software libraries, all these different things that actually come into play in terms of delivering performance. And that's what makes comparing system X versus system Y extremely challenging. So the goal of today's talk is to really kind of help you understand and uncover that level of complexity so you start appreciating why you really need to effectively build a new scientific instrument. In my head, the benchmark is like a scientific instrument, like a microscope that allows you to kind of understand what's actually happening underneath the hood. Now, if we just want to talk about this at large, right? So let's say if I talk about, just kind of computer vision applications, this is a very widely popular chart from, related work. that shows, what's the accuracy that we're getting for various kinds of models with respect to the computational performance. A fairly dated chart, but nonetheless, it kind of makes this point, which is that there's a rich array of different kinds of networks that are in the ecosystem for just one particular task you want to do. And these things offer a rich array of trade-off, right? So I can get really high accuracy if I'm willing to really push on the computational burden. Or I can get some sort of, nice little, ResNet 50 is one of the poster child applications people like to study. Why? Because honestly, it sits sort of like perfectly in that knee of the curve where between accuracy and performance trade-offs. So, but that's one particular application. Now, these applications come with a lot of different trade-offs. You have to understand how you're deploying models. Deploying, a computer vision model on a smartphone is wildly different from deploying the computer vision model on an autonomous car. Two completely different things, exact same task, and I'll show you why that's so widely different. What that then means is you have to systematically understand how things are being deployed for the exact same task, for instance. And of course, there's an incredible level of complexity in the systems task. So even if you just kind of say, hey, I want to look at computer vision, when you look across the system stack, going from applications, then, when I give you a number which says, okay, system X performance is this, system Y's performance is that, I really have to understand that with respect to what data set are you actually using to study, because that accuracy number really is dependent upon the data set. Then, of course, there are multiple different models behind the scenes, multiple different frameworks. You have lots of optimization libraries, a lot of levels of performance variability, even including the system stack around the operating system. The scheduler actually ends up impacting the performance of the particular hardware design. Now, this is where if you want to try and tackle this level of complexity, you really need to build an industry-wide or industry standard benchmark, which is extremely hard to do, but it can be done. So in the last couple of years, what we have done is built this benchmark called MLPerf. Now, for folks who are generally familiar with computer systems and so forth, historically, much of the innovation in microprocessor innovation, like the Intel, the AMDs, and so forth, much of that innovation was truly driven by benchmarks. There are benchmarks like TPCC, SPEC, LINPACK, and so forth. There are plenty of different benchmarks that have come before this that have been driving much of the innovation that we see, because benchmarks are like a competition, right? It's like getting ready for the Olympics. You put together your best athletes, you kind of come up with the best system, you train really hard, you figure out how to really squeeze out every single bit of millisecond out in the performance. But in order to be able to do that, you do have to have a very systematic framework, and that's effectively what MLPerf is. What I'm going to talk about today is kind of like, what is MLPerf? Because it's an industry standard thing, and you should really know about this, and it spans everything from the data center down to the tiniest little IoT widget. So in terms of measurement of power scale of systems, you're talking about megawatts kind of systems down to microwatts kind of systems. And so I'll talk about like what MLPerf is, and then I'll talk more technically about how do you kind of build a benchmark? What's actually involved in this process? It's not like just kind of taking an apple and an orange and kind of just looking at them, right? There's a lot of nuance about what those fruits really are. And so I want to get into a little bit about the science behind benchmarking, and then what happens after you kind of study these systems where we are today. So MLPerf, long story short, is like, it's a consortium that's made up of multiple different companies that we brought together, including academia. And the key goal of this benchmarking standard is to kind of put together, workloads that focus on training and inference benchmarks. So, as it's an ML class here. So, without data, there's no ML. Practically, that whole thing doesn't exist, right? So everything kind of builds off of data sets that we have. So we take large public data sets that are available. Sometimes we work with industry to try and get them to give us data sets under benchmarking licenses to be able to, really push the models. And what we do is we create, training benchmarks. So these training benchmarks essentially are a suite that are specifically designed to study machine learning training systems. Then we have inference benchmarks, much like the TinyML systems, where most of the time we're just doing inference. We're not really doing any sort of on-device training. And the goal of these benchmarks, which I will open up the hood on in a second, the goal generally of having this sort of data sets and these workloads kind of coupled together is that we want to be able to identify a key set of ML tasks and models that would be representative of what's actually happening in the industry, that if you come up with a solution for this problem in terms of a model or a system, then you can actually advance the field forward. Now, as I said earlier, deploying a computer vision model on a smartphone is wildly different from deploying a computer vision model on an autonomous car or in a medical setting, because those scenarios have fundamentally different requirements in terms of what the accuracies and latencies are going to be, right? On a smartphone, I don't care if I take 1,000 pictures when I click the button. I just care about the one picture. Really, that's what you and I mostly care about, is that one amazing picture we can get. In an autonomous car, it's a little different because you probably have 16 different cameras that are taking a global picture, 360 degrees view, and all of that data has to come in, quote unquote, at roughly the same time. So then you can figure out where the obstacles are and make a intelligent decision on whether I'm going left or whether I'm going right. Moreover, I need to be able to see pretty far into the distance in the image, right? So the resolutions matter. So I'll open up the hood around what these scenarios are. How do you understand how ML is actually being deployed in the wild? Now, I'll talk a little bit about, what are the rules you need to have, because benchmarking of ML systems is quite unlike anything we have seen before. It's a fundamentally new field. So we really need to understand what it means to kind of, introspect these systems. What are the kind of metrics we need to have? And if you're not careful with the metrics, someone can come and say, hey, I've got this amazing TinyML little widget, and you would end up making the wrong decision. Why? Because you're looking at the wrong metric, because metrics are really what drive, buying, purchasing decisions, or understanding which system should we get for the kind of problem that we're trying to solve. And of course, I'll talk a little bit about how we get results and all that good stuff. So why is something like this actually important for the ecosystem? First and foremost, any field, doesn't really matter if it's ML and whatnot, right? What fundamentally matters is that you have to have performance result replicability, because that's what really drives innovation. We all, might get in a boat and then, start stroking towards the same direction, but it's a measure of like, how precisely are you calculating how far ahead any one particular system or, ecosystem is. And for that, you need to have result replicability. Then you need to study representative workloads. Why? If I'm going to be making a purchasing decision, let's say for the next big data center, if you're studying smartphone workloads and I'm trying to build a data center, well, those are two completely different workloads, right? So the way they behave are different. So that means like, the workload is going to stress the system in a different way. So I need to be studying and benchmarking representative workloads that would actually be in my deployment that I care about. So then you need to identify what are those representative workloads. They have to be something that's in the cutting edge space. Then of course you have to drive innovation. The whole point of having benchmarks is not so you can just say comparing apples, apples and oranges. It's really about kind of moving the field forward, right? So benchmarks prove to be a very critical point. A bit tacky, but an example I can give you of this is kind of thinking about it from the perspective of, if you want to go to the moon, you have to identify all the different tasks you have to do, and you have to do well on those tasks to be able to get the rocket to the moon. So you have to identify what those pieces are in order to drive ML system progress. Then, of course, you have to have, provide meaningful measurements. You have to collect the right kind of data. And it has to be something that's accessible both to commercial entities and research, because ML is very much an academic thing still, right? So academics need to be able to take part in these benchmarks. And you have to keep the whole pricing affordable, because otherwise, benchmarking can be a very costly affair. So let's start talking a little bit about on the technical side about what does it mean to create a benchmark. Now, ML is used widely across the ecosystem, right? It's used in many different application areas: computer vision, language, audio, commercial applications, gaming, and so forth. So you can't boil the entire ocean and say, hey, I'm going to study this entire space and then give you a number. That doesn't make any sense. Moreover, I probably don't care about certain areas. If I'm building the Ring doorbell, I have zero interest in reinforcement learning, or I have zero interest in some sort of audio device, right? But if I'm building an Alexa, I care a lot about the audio section of things, right? So you kind of have to somehow identify what's this wide ecosystem down there and try and distill that space down. So here I'm showing you different modalities. Now, even if I were to pick one particular modality like computer vision, well, even within computer vision, there are many different ML tasks that we do, right? You might be doing classification, you might be doing, detection, you might be doing segmentation. Even if you pick segmentation, I can still say I'm doing instance segmentation, right? Which is kind of uniquely identifying individual pieces and segmenting individual things, not the whole thing. So there's a lot of nuance in terms of what kind of applications you're looking at. Now, after I figure that out, so let's say I kind of distill this whole big first row down into a handful of things, right? Then you've got a rich number of different models, as I showed you with computer vision, a whole bunch of different models. So how do you decide which model to pick to benchmark, quote unquote? Then which data sets and what are the right metrics, right? Because there are multiple metrics for, and you look at computer vision, it's loaded with a whole bunch of metrics. And so what metrics do you pick? So these are the kind of things you really have to kind of distill, which I'll talk about more in depth. So how do you sort of benchmark, right? You have to have some sort of framework. So what, MLPerf, like as an industry consortium generally does is, there's a key set of kind of research questions that we go after. So what is the definition of an ML benchmark task? At the end of the day, an ML is like an application, right? There's a whole bunch of stuff happening. So you have to kind of break it down. And so I'll talk about what is the definition of a task. then how do you sort of pick that task? Is it state of the art, or is it something that everybody understands? What are the metrics to have? And how do you study implementation of these models you might pick to study? Because there's lots of differences. If I run something on PyTorch, it's not the same as running it on TensorFlow. It is not. Even you take the exact same model, I guarantee you 99% it's not going to be 100% mathematically equivalent. So you have to deal with that, because otherwise you're effectively studying apples and oranges. And then lots of different domain specific sort of optimizations that are done, right? Quantization, retraining, hyperparameters in the training setup. All of these things affect how we decide things. So let's step through each one of these a little bit. So what's the definition of an ML task? Normally, when you take ML and you take a model and you try to use it in production, you're not just kind of sticking a model. What you actually do is you put it as part of an integrated pipeline. So for example, let's just take the camera, right? Or like on your smartphone. It's not just a neural network running, right? The neural network is a portion of the vision pipeline that they have. So the first thing that happens is like, when you have a picture kind of come through from the lenses, it goes into the ISP, the signal processor, the image signal processor. So that ISP is basically then processing, doing some image manipulations to try and clean it up. Then it's typically fed into a neural network task. And, it might be whatever it's doing. It might be super resolution or whatever it's doing. And of course, it's not just one model that might be running. There might actually be multiple models that are actually running. So if I take a picture of some sort of task, like let's say I take a credit card. If I take a picture of a card, right, there's usually a name, a cell phone number, and all that stuff. First thing is recognizing that, hey, it's a card. Second thing is invoking the right language model to be able to do translation of, oh, this is the name of the person and so forth, if you want to extract information. So a lot of stuff is actually going on. So you have to define what about that task do you actually want to benchmark. In the context of this particular talk and MLPerf, it's typically just one model. And we'll look at what are those models. So now, okay, we say we're going to pick one particular model, then the question becomes like, how do I pick the right model? Because as I showed you in that computer vision task, there's a whole range of different models. So you have to think about the maturity. Do I pick something like AlexNet, which is the gold standard, everybody knows about it and so forth, but nobody uses AlexNet in production? Or do I pick something that's, just come out? Like, if let's say if it's EfficientNet, 4 or something like that, that just came out, do I use that? Well, kind of, you want something that industry is really using in practice, because you want to be able to, make commercial sense out of it in some capacity. So you want the cutting edge, but not the absolute bleeding edge from research. Then, of course, when you talk about a benchmark suite, you have to make sure you cover a rich array of different tasks, right? Remember, I showed you this audio, vision, and all those different areas. You have to cover that whole space. Moreover, at the lowest levels from a computational standpoint, because that's what you're really studying from System X versus System Y, you need to make sure you're stressing the microarchitecture of the particular chip in a particular way. To do that, you need to have a balance of different kinds of fundamental building blocks. So the transformer with attention is one way of kind of running neural networks, right? That's one type of Lego piece. But there are other Lego pieces like LSTMs, RNNs, and other kinds of network architectures that we have. So you have to kind of pick all those different Lego pieces to make sure that you start stressing the hardware in different ways. Then the complexity, right? Is the network really complex, or is the network relatively simple, right? So again, I could do something like SSD versus mask RCNN, and the image resolution might actually be different. Like in an autonomous car, the image resolution is maybe around 2 megapixels. In a medical case, it's around 4 to 8 megapixels, because I don't want to miss the cancer and I have to make sure I really spot it. So the image resolutions change. If the image resolution changes, that has a direct impact in terms of what the hardware's capabilities need to be. And of course, do you actually have a public data set to drive all of this? Because as I said earlier, without data, there's nothing. Now, I'm an old school kind of guy. I love going back to the, where the original things have started. So right now, MLPerf has progressed into version 4, which is, pretty far ahead. So it's, about 4 or 5 years. But back when it was originally starting off, so this is kind of like after things kind of started maturing, you'll see that, the community had kind of gathered different kinds of benchmarks. There are lots of different vision tasks, lots of language class, commerce. So you might be saying, hey, why are you looking at multiple vision tasks? You said that, Vijay, like, you got to have this diversity, right? So why am I looking at multiple vision tasks? Well, that's because, you need to have different kinds of vision tasks, right? So I told you there's a lot of variety in there. So image classification, detection, even within detection, I said there might be different kinds of detection. You might use lightweight detection, things like, SSD model, versus like, something like you're going to deploy in, some heavier instance, like an autonomous car or something where the resolutions need to be higher and so forth. So you need to have multiple varieties of those different kinds of networks. This is on the training side, right? So this is the training side. And the most important thing I want you to focus on is this quality target. One of the key things is to understand what is the actual quality target? And industry often sets this out as part of the MLPerf benchmarks. It tells you what rough quality target you need to hit, right? And so, this is an old school number, but for ImageNet, for instance, like, 75.9%, if you hit that, that's the training time. So however long it takes for you to train, you have to hit that. Otherwise, you don't even qualify, because it's all about accuracy at the end of the day in these systems, right? That's on the training side. Now, if you look on the inference side, again, you have lots of different areas that the benchmark is kind of covering. Again, you have heavy models, you have light models. As I said, heavy models, for instance, have a higher resolution. Light ones have very small image resolutions. Like your camera is typically working with a 300 by 300 pixel, if any at all. And from one version to the other, benchmarks continue to improve. That's the important point down here, is that benchmarks are never a done process. You have to continuously keep improving them. So from where we started to where things are, actually, again, this is an old slide. Things have come a long way from then. Again, the most important thing here, in addition to this image resolution, is again these quality targets. What are these quality targets? As you can see down here, it says like FP32 is the baseline, but sometimes you tend to do optimizations which cause you to lose, that's the trade-off you make often in machine learning systems. You compromise accuracy for some sort of performance. So you can see that, the accuracy is like 99% or whatever the baseline model that kind of comes in with the benchmark. In some particular cases, the accuracy requirements are 99.9%. Why? Because you're trying to emphasize that in certain deployments, you care about that accuracy much more. And getting performance at that really stringent accuracy as compared to like FP32 means your optimizations have to be really good. You cannot compromise accuracy just to get better performance. And I'll open that hood with some examples in a bit. Now, inference is also very complicated because inference, spans the entire spectrum from, mega data centers down to the smallest IoT little widgets, right? So all of these have very different kinds of, requirements. And I'll talk a little bit about smartphones. Like if you look at the smartphone ecosystem, again, you have different kinds of networks. And same point I'm making here, but you can see that the image resolution, right, for these different vision tasks, the image resolution is consistently very, very small, right? And the accuracy numbers here, that's the point I really want to get to, is that the accuracy numbers in here are inherently different, because mobile devices typically don't have that stringent, because you really have to kind of balance this performance versus, power issues, right? You can't just kind of crank up performance in a mobile device because the phone's going to heat up. So you tend to have much more room. And this kind of is reflective of understanding what is the level of tolerance people are willing to accept in industry. Mobile is also generally a much harder beast. Mobile people think, data centers are the really hard problems. I often tell people, if you work on mobile systems, you will really appreciate what it means to have a very rich and complex SoC. The Apple iPhone, for instance, has about 40 to 50 IP blocks. The Orion, that the Meta glasses that came out recently, that actually has over 60 different individual processing elements, all of which together make up the device. So when you start getting into that, you tend to have lots of different hardware engines internally. It's not a single CPU or something. On a mobile device, when you run your camera, the inference is actually happening on a bit on the DSP, the digital signal processor. It's happening on the GPU, and sometimes it happens on the CPU. How that is orchestrated is, up to the software layer, right? So the hardware has all this capability. Often when you look at the MLPerf results, the results actually come out from this collection of different IP blocks that are exercising this. Lots of different software frameworks, and these software frameworks can actually dramatically impact the performance, because developers often have to pick which configuration of knobs they're going to enable. For instance, like, if you have an app that you're having a model deployed in, then you have to think about, is this something that is actually going to run directly on the platform framework, or do you sort of bypass this and run this? If you use a API layer like the NN API, which is stock and that's typically shipped with every Android device, performance can vary significantly on the exact same device. So here I'm showing you what the performance on an Android device can be if you're using the custom accelerators supported with the CPU versus you use some sort of high-level library that actually enables it. This is because the library actually has a bug that's well known. And so you can see that the performance is like, over 700 milliseconds latency if it happens to use a specific operator that's inside the network. Of course, these things can also be packaged in many different ways. Like if you buy a Samsung phone, let's say, or you buy a Huawei phone, the way these things are deployed comes through the vendor runtime, which are highly specialized. So Core ML is a runtime that comes specifically from the Apple guys, right? So it's highly specialized for it. Or you can have like, really specific, a highly custom backend, like for first party applications where you can really couple things down all the way down to the hardware. So lots of different deployments within the exact same ML system. So when you get performance and someone asks you, hey, how does phone A compare to phone B, system X versus system Y? You have to understand all these different variabilities that are deep inside the system stack, right? So again, you're shipping things onto, if you're talking about mobile, you're shipping things onto, a Play Store. So when you're talking about putting things in the Play Store, you often know, okay, I want to do computer vision, but I don't really know where the app is going to run. It can potentially run on a whole bunch of different Android devices. All these Android devices have widely different, processing capabilities underneath the hardware. So you don't really know what performance you're going to get. So this is why developers in the AI ecosystem get very, very cognizant about how things are actually deployed. Ultimately, I'm talking about things at the lowest level of the system stack, right? The hardware, the software, the libraries, and all that. But at the end of the day, whoever's packaging up the phone, right? So when Google packages up the phone, even though they have a Pixel processor, the Google Pixel phone division will actually decide what models they want to run and how they want to run and when they want to issue the software updates and so forth. Long story short, performance is never as simple as it seems. There's an incredible level of complexity that you actually have to unravel. And in order to be able to unravel, you really have to understand what's going on underneath the hood. So just to kind of give you a snapshot from one set of results that officially came in, when I say results, it's like, Google Pixel, Android, the very different Androids, the Huawei phones, the Samsung phones, and so forth. All these are competing. And so they might, study, these different networks, right? So you have lots of different models. So let's say, the benchmark has these 4 particular tasks in this particular version. There are many different numerics that are involved, right? You're taking this class, so obviously quantization and so forth are things that you probably picked up. So there's FP32, which you might want to run. Some cases for NLP tasks, typically FP16, precision is needed, even though you might have in-date quantization support. So people will actually pick different kinds of numerics in order to run the networks differently. Just depends on what, how they have optimized the system stack. And there are lots of different ML frameworks to pick from, again, in the mobile ecosystem, and lots of different hardware capabilities at the lowest levels of the stack, right? So all of this cross product makes understanding that system level design is extremely complicated. Now let's kind of go a little bit further down into the TinyML thing, and TinyML obviously gets even crazier. Why? Because these systems are extremely resource constrained, as you know, right? And I'm showing you a baseline of a Raspberry, which is kind of considered like a typical computer, right? And you can see that if you look at the memory footprint, a Raspberry might have something like 2 gigabytes, but most of these embedded microcontrollers have only tens of kilobytes of memory, right? So you need to be able to benchmark them, and then their scenarios are going to be different. As you know, TinyML kind of uses things like keyword spotting, visual wake words, doing anomaly detection. These are not stereotypically kind of examples of typical examples of what a data center would do, but these are highly domain specific. So which means that when I want to study a particular area and benchmark those systems, then I need to be able to take a quick look at what are the core tasks that are involved in that particular space. So you have to kind of identify those tasks. So let's say we identify all these things. Now let's talk a little bit about where things can get really gamified, where you have to be very careful about understanding the performance results. So I'm going to give a little bit of hint towards, training and inference systems. If you look at training, for instance, right, the key thing is, it's not about just performance of the system. Naively, if you're looking at, much of the computing systems, traditionally, we tend to think about just performance. But as you know, in ML, you really have to worry about what the quality is. The accuracy comes first and everything comes after that. It does not make any sense for me to say that I can give you 2x performance improvement. Instead of 10 seconds, I can do it in 5 seconds. However, I might be botching up, whether it's a cat versus a dog. Well, at that point, do you really care? I'm like, no, give me the correct answer first and then work backwards. So you really have to kind of look at both of them, in close proximity. Think about it, a very conventional thing, right? Let's say I give you system X versus system Y. And I just come to you with this amazing number and say, hey, you know what? You should totally buy system Y because system X is down here. It's images per second. It's less than 1,000 images per second. If you buy my system Y, I can give you, a throughput of over 20, over 2,000 images per second. Off the top of your head, your first reaction is going to be like, yeah, damn it, I want to buy that, high throughput engine. Why the hell would I want to pay for something that is like slower? That's because if you don't look at the accuracy implications of it and you don't understand where the throughput is coming from, then you're making a naive choice. Why? Because if my batch size is really sort of small, right? Because I'm cranking up the batch size down here, the number of images that are kind of continuously looking at. Obviously, if I increase the batch size, I can get a much larger throughput through the system. But whenever I increase the batch size, my accuracy actually drops. What this means is that for me to hit the target accuracy, it takes longer. So if you buy a system like this and you put it into production, training ChatGPT might actually go from taking 3 months to 6 months, practically doubling your electricity bill and all these things. So these are the kind of nuanced things that you really have to be careful when people report numbers. And there was a lot of this confusion going on in the industry, which is why a benchmark was needed. Because think about it. At the end of the day, what you really want is you want fewer epochs in your training cycle. You want to be able to train really fast because that is what, it's getting to the quality, right? But to do that, you typically have to use high precision, like FP32, FP16, and so forth. And you have to use lower batch sizes, right? So that's typically what is going to get you to the most efficient training. But that's not always the case that you have to be at FP32. You don't want to be at that extreme either. Now, if I want high throughput, I would use lower precision because arithmetically it's much simpler to deal with things and use a higher batch size, as I showed you. So my point is, if I was just selling you the system from a pure performance standpoint, I would put you on the left side and I'd just, do a little bit of a snake oil dance around you, right? But if when you put it into production, what's going to matter is how long did it actually take to train. So you sort of have to understand these right metrics to look at. And this is why I say that, benchmarking ML systems is a bit of a science. You have to understand what's really going on behind this. Then, of course, there are lots of different ML frameworks, which means it makes it really hard to kind of, you have to really understand what happens when I go from TensorFlow to PyTorch. For example, if you do object detection, there's a thing called NMS, non-maximal suppression. It's just a simple library function, but the way it works actually has a downstream impact on how the rest of the network will actually behave. So because those implementations are actually not part of the network, it's actually a library call that it's dependent upon what the frameworks, how they choose to implement it. Training has also got a lot of different hyperparameters. So, you have to be very careful about this. If you're not careful, I could actually tell you, hey, my system X is really powerful, but in fact, it's got nothing to do with system X. I just played around with the hyperparameters, and because these are stochastic systems, I can pull a quick one on you and say that, oh, my system is actually really good. But in fact, no, it turns out you just did a hyperparameter search and you searched all the right configuration parameters for the network. So you have to kind of be transparent about this. And if you're not careful, you can get tricky in this. And of course, these are stochastic systems, so which means you have to think about repeatability. So for example, here I'm showing you a workload where if I run it a few times, right, and I use different seeds, you can see like the variability is quite strong, right? So if I use seed one time it takes only about 30 epochs to converge. Another time it takes over 45 epochs in experiment 3. So I have to think about, is this network inherently stochastically, sensitive, or is it like, no, it's like ResNet, which is on the left, which is very nice and stable. So I don't have to do tons of experimentation around it. So that's on the training side. There's much more I can talk about. Let's talk a little bit about the inference side, how to understand inference. When you talk about inference, again, I was making this point that, inference is kind of like, it's deployed in many different systems and they have vastly different characteristics. If I look at a smartphone, I'm just kind of taking a picture one at a time, right? And so if I care about that, it's a single stream. There's one picture at a time. But if I'm looking at an autonomous car, then it's a multi-stream workload because there are multiple different camera feeds that have to come in to make the decision by taking a single global view. So it's a multi-stream. There are multiple different input sources I have to handle at the same time, throughput oriented. Servers are more, they have this Poisson interval distribution. Requests don't kind of come in at a steady rate like in a car. They kind of come in based on user activity. And of course, you have offline things, which is like, just kind of offline. Like when you're sleeping, your camera is getting, your photo album is getting indexed with, faces and so forth. There's no real-time aspect there. Why am I explaining this? This is because the metrics actually matter. For example, if I'm doing single stream, then what I really care about is the latency. If I'm doing a car, latency still matters because I have to respond. I'm physically moving, so I have to respond to what's actually happening in space and time. So it's a bit of latency bounded throughput metric. So the metric is slightly different. Server is, it's again latency bounded throughput, but the metric is, the quantitative number is different. Offline is just raw throughput. So all of this basically means that I have to be very cognizant about understanding how a model is being deployed and where is it being deployed, and then use the right metrics to study it. And as I mentioned earlier, re-implementation, often, benchmarks come with a certain set of weights, and there's a system that's actually running it. And that's kind of getting, it's being subjected to different kinds of loads based on the scenarios, and then you measure what the performance is. You tend to do a lot of optimizations when you're doing inference. So obviously quantization is important, but when you do quantization, you have to understand how you're actually doing the calibration of the system. Because quantization is based on, how you map the values down. And typically to do that, you do a calibration data set run. So you have to understand, you can't let people get crazy about the calibration runs, which means you have to typically give, hey, here's the calibration. data set, and then you should use this. And often when you do quantization-aware training, quantization, you also tend to do quantization-aware training, where you tend to modify things a little bit in the network in order to regain the accuracy from dropping from, say, FP32 down to int8. But when you do that, your retrain can potentially change the network architecture. So you got to be careful about that as well. So long story short, I just want to give you, a couple of quick highlight results of why do all these things? Why do people go nuts on benchmarking, TinyML systems and big systems and so forth? It's because once you start benchmarking, progress really starts showing. So here I'm showing you, between 3 iterations of, just benchmark way back then. You can see for the exact same hardware, you get massive improvements across from one version to the other for the exact same network. The reason is because software starts getting better because now things are getting measured. So people push the software really hard. And this is an old result, but nonetheless, it shows you, what the performance capability can be across rich kind of hardware, right? You have to support FPGAs, DSPs, CPUs and so forth. And the benchmark is kind of built for that. And at this point, there were about, 50,000 results between training and inference and so forth. So there's a lot that's actually kind of happened since, these original results. Again, I'm an old school guy. I love the originals. So what's the impact of building these benchmarks, right? The nice thing is that you can basically define what the core set of problems are, then you can align the industry behind a clear set of metrics. That leads to healthy competition where you're trying to build the next best engineered machine learning system, right? And the results will basically show you what is actually working, what's not working. And this, in a way, kind of forces innovation at the hardware and software layers, basically. And that's sort of extremely critical. So, when you kind of build these benchmarks, you often have to have some sort of ecosystem to support it. So, companies become members of these things, and then we end up building the benchmarks progressively because benchmarks have to continuously be improved. We have to build data sets that challenge the models. If the data set is not challenging enough, the model will converge very fast if you're training. So here are examples of data sets that we've kind of built. These are extremely large data sets. And one of the key things is to kind of focus on making sure that it's commercially licensable and useful. We do this for IoT devices. We've done this for multilingual spoken words corpus. So lots of data sets kind of need to be built. Long story short, that's the point. I want to kind of wrap up with this new kind of thing that I want you to think about, which is like data perf. ML perf is kind of really focused more on kind of benchmarking the code side, the model side, but in data perf, we're really trying to study the data. We want to benchmark the data. Why? Because if you kind of look at it, a lot of research is, research and effort is being put, billions of dollars are being poured into building ML models. But data is what is actually driving all of this engine. Data is the code, right? So in my head, I often go around saying this, data is stupid. It's got nothing to do with the models. What that means is that you really have to study the training data, the test data, and the algorithms that can allow you to construct these data sets really effectively. So classically, what you do is you kind of lock the model, like you try to improve the model and you take ImageNet, something like that, that's kind of locked in, right? You don't change it. In the data-centric paradigm, what we're trying to push for is essentially lock the model. The model is really not that important. Once you get a decent baseline architecture, it doesn't really matter. In fact, like if you're doing TinyML systems, I would almost say efficiency is so important. So just lock the best network architecture for the TinyML device and then churn through the data. That's a much more effective for getting a state-of-the-art result, in fact. But then this gets into, what are the ways of, training data? What are the kind of algorithms you need to build? How do you benchmark all of this stuff from a data standpoint? Opens up a whole new world, much like, all the stuff I talked about with ML benchmarking from an ML perf standpoint. And often, as I was mentioning, you need to have an industry sort of consortium or something that kind of keeps these benchmarks updated, builds the data sets, and kind of establishes all these different best practices that you need around the metrics and so forth. Because it's super easy to say that system X is better than system Y on the wrong set of metrics. And this was one of the biggest places where industry had burnt an incredible amount of money in the early years, right? Around 2015 to 2020, a lot of money was being spent. Everybody was very confused. Hey, why am I not getting the result and so forth? So it's hard to believe this, but even when there are billions of dollars involved in this process, things go awry amazingly well if you don't actually have, some sort of curated methodology. And so this is why we still write state-of-the-art papers as a consortium, that collaborates widely with academia. ML Commons, helps build a lot of these benchmarks. So I encourage you to kind of check out some of these papers. These are just a handful. But if you actually really want to get into this, it's like I know I went through a lot. Actually, I'd encourage you to kind of check out this benchmarking AI chapter on this open source machine learning book that I've been working on. but this chapter really gets into this nuance of understanding what's the history of benchmarking. How do we have to kind of think about benchmarking from an ML system standpoint? How do we think about benchmarking the models versus the data and so forth? So that's all I got. And last but not least, one thing I'd request is like, I'd love, I often do a lot of outreach around this sort of an ecosystem. I'm really passionate about making cutting edge knowledge and all that stuff globally accessible. So I've been kind of working on putting this open source, resource for people. And lately I've been kind of raising funding and so forth from, industry consortiums like Edge AI Foundation and so forth. So every GitHub store is basically one student learning the material or, one company sort of supporting, throwing a fair bit of money behind the scenes in terms of supporting scholarships and so forth. Of course, not at Harvard or like at UPenn and so forth, but more for the global South. So I would really appreciate if folks could just kind of take a look at this. If you like it, give it a get started a long way. So back to you, Rahul.
Yeah, thanks a lot, Vijay. This was really great. We have time for one or two quick questions. So I'm just going to pass it on to the class with ML benchmarks. But at least first you can tell Vijay a big thank you to
Hey, folks.
So not just for giving this lecture, but for giving us all the lectures. Okay, so for this class, and you can see if you were to mute him and just play some rap music, you can see him just jumping around with his amazing energy. So any quick questions you guys have with the benchmarking that you'll have to do for your projects also, right? So
Oh, that's cool. I didn't realize they actually have to do some benchmarking.
yeah. I mean, they have to. All right, no questions. Okay, I think they are a little bit out of time, but I'll ask you a question or two. But thanks so much. And yeah, you guys are free to go, and we'll have office hours in 10 minutes. Yeah.